if you stare at that, you can see something interesting. The shape of this little triangle is the same as the shape of this big triangle. They're different sizes, but same shape. So that means the ratio phi divided by 1, which I've written over here, has got to be the same as the ratio 1 plus phi divided by phi, because they're in proportion to each other. So phi is to 1 as phi plus 1 is to phi. So that's the magical property of this number phi. And if you want, you can take this equation and multiply both sides by phi. So over here on the left you get phi squared, and on the right, I just did this to get rid of this denominator here, you get phi plus 1. So the equation that the golden ratio satisfies is that phi squared is phi plus 1. So it's the number, it's a number that's positive, and if you square it, it's the same as adding 1 to it. That's what it is. If you know how to solve a quadratic equation, you can solve this quadratic equation and figure out what it is. And it turns out to be 1 plus the square root of 5 over 2. So the 5-ness of the pentagon actually sneaks into the 5 here in the golden ratio. And you could think a lot more about why that really works that way, but it certainly does. And then you can plug it into your calculator and you can figure out what it is. And it's 1.6180339 ... And then if you don't believe me when I say that phi squared equals phi plus 1, you can take that number and you can square it, and your calculator, which never lies, will tell you it's 2.6180339. So it's really true that it satisfies that equation. But it's a marvelous number. It shows up in lots of different ways, and it has lots of nice properties. For example, I can take this equation here and I can divide both sides of this equation by phi. So if I divide phi squared by phi, I'm left with phi. If I divide phi by phi, I get 1. If I divide 1 by phi, I get 1 over phi. So phi is 1 plus 1 over phi. Or in other words, if I just fiddle with this equation a little bit more, 1 over phi is the same thing as phi minus 1. So the other nice thing about this number phi is if I take its reciprocal, 1 over it, I just get 0.6180339. So it keeps sort of showing up when you keep fiddling around with it in different ways. That same decimal expansion shows up. Now, there are lots of interesting things about it, and probably the most interesting thing to me has to do with this idea of continued fractions. So the Greeks liked to study fractions in a certain way called continued fractions, and here's how it goes. So I'll just take some number, some fraction, I made up some crazy one, 74 over 32, and then here's what we'll do with it. We'll divide 74 by 32, and we'll get 2 plus some leftover stuff that's smaller than 1. So we get 2 plus something, and that something just happens to be 10 over 32. And then what we'll do is we'll take this leftover part, this remainder part, that's less than 1, so we'll write it as 1 over something that's bigger than 1. So 32 over 10 is bigger than 1. And then we do the same thing. In other words, this number is bigger than 1, 32 over 10. So now we write it as a whole number plus some leftover stuff. So 32 over 10, you can see, is 3 plus 2 over 10. So then what do? We just keep doing the same thing. 2 over 10 is the same thing as 1 over 10 over 2. And now we take this number 10 over 2 and we write it as a whole number plus some leftover stuff. But in this case, it stops. 10 over 2 is a whole number. It's 5. So we quit there. And so that's called the continued fraction expansion of this fraction, and it quits at this particular point. So if you take any ratio of whole numbers, you can play this trick to it, and you get this way of writing it called its continued fraction. And it stops at some point. Euclid, there's something called Euclid's algorithm that you may have heard of if you've taken fancy math classes, and it's based on this idea that it stops at a certain point. But if you take the number phi, it never stops. Because, as I said, phi is 1 plus 1 over phi. That's one of those equations I wrote down. So if you're some poor schlep who's trying to work out the continued fraction of phi, you'll say, okay, phi is 1 plus 1 over some extra stuff. Then I have to do the same continued fraction trick to that phi. Well, what is that? Well, phi is 1 plus 1 over phi. And then I have to do the same thing there. So I get 1 plus 1 over 1 plus 1 plus 1 over phi, and it goes on forever. So it never stops. And if you have already convinced yourself that when you have a fraction, a ratio of two whole numbers, that this process must stop, then with this number here, where it never stops, it can't be a ratio of two whole numbers. So it has to be what's called an irrational number. There's a story that when the Pythagoreans when there was some Pythagorean who first proved that some number was irrational, and they say that he first proved that the square root of 2 is irrational. The story goes that some other Pythagoreans took him out on a boat and drowned him because they liked rational numbers so much. They just didn't want to hear about this. It was like an unsuccessful cover-up of the existence of irrational numbers. And the way that the story is usually told, it was the square root of 2 is like the first one that they found that was irrational. But it's possible, since the guy drowned, who knows what he really discovered. It's possible that it would be phi that he discovered was the first irrational number, because it's so easy to show that it's irrational if you know about continued fractions, which the Greeks did. And in fact, the Greeks really liked proofs using geometry. They didn't really write down fractions the way we did. But in fact, you can even just look at a pentagram and stare at it. And if you stare at it hard enough in the right way, you can see from it that the continued fraction expansion for phi never ends. And so something that some people wonder is whether just that would be enough to let them see that phi was irrational. So how do you actually... Well, I don't know if the Pythagoreans knew this. I'm just sort of making this up. Okay. If I was a typical historian of mathematics, I would just claim it was true. Mathematics is one of the hardest subjects to do the history of, because if you see something is true, it's just hard to believe that someone else couldn't see it too. And so the historians of mathematics say, well, like, of course they must have realized this. And so they just make stuff up, in other words. Since I'm not a historian of mathematics, I guess I'm not allowed to do that. But I'll still make up this thing here. My friend James Dolan drew this picture. So what is this thing? Well, it's just a big black pentagram, but I'm not trying to initiate you in some satanic cult. I'm trying to show you something here. Namely, if you take some of the corners of this big black pentagram and start connecting them up with lines, you get these lines, and those lines form other pentagrams. So I just got this blue one here by connecting up the corners of the black one. But then I can do other stuff. Let's see, what's the next good thing to do? Well, for example, I can take these two corners of this blue one. I can draw a straight line through it, which is this green line, and I can extend that all the way out to here, and all the way out to here, and so on. And then I can start connecting up those things with lines, and so I get all this stuff. So if someone hands you a picture of a pentagram and all you have is a straight edge, you can just start drawing more straight lines, connecting dots that you already see, and you can form this whole big picture. And you'll notice that it's full of pentagrams of all different sizes. In particular, for example, you can see this blue one, and then there's a smaller green one, and then there's a smaller blue one, and then there's a smaller green one, and then there's a smaller blue one, and then there's a smaller green one, and they shrink away forever like that. And the interesting thing is that the ratio of the sizes of, say, like this green one, this green one here, to this bigger blue one, the ratio of the sizes of two of those is the golden ratio. It's phi.